All right. So 18.2, last section of the year. And it is a pretty easy one. So if you pay attention, you cannot go wrong with this section. The answer is either left or right. You got a 50-50 chance. Okay, and it's basically once we've reached the equilibrium that we've been talking about, the balance point where the forward and the reverse reactions are equal rate, then you can do something that messes with the system, and that's called a stress. Okay, we know about stress now because any kind of change that you make is going to make a stress to the system. And then it's going to adjust to try to relieve that stress. So we are going to shift in a way that tries to lessen the stress. That's a life lesson there, right? Whatever life throws at us, we're going to try to adjust ourselves to lessen the stress. We can't get rid of it, unfortunately, but we can deal with it. Okay, so what are the changes that we can make? The stresses that we can put on the system are changes in concentration. So basically adding something. So I'm going to come over here and draw our equilibrium system again. So we had our reactants, which were going down. Okay, I'm going to draw a little different one this time than the last one. Okay, so they decrease fast initially, and then the slope kind of levels off. And then when it stops changing over here, we're at equilibrium. And the products are going to start at 0. They're going to increase at the same rate that it's decreasing. And then they're going to level off and remain constant right here. Sort of constant. Okay, so this is different than the last drawing. This is my product, B, and that's going to be over here on this side. And then my A is my reactant. Okay, so A is turning into B. And let's show the reversible reaction sign. So it can go to the right, or it can reverse itself and go to the left. So A is turning into B, and then B turns back into A. When the two rates, the forward and the reverse rate, are equal, we're at equilibrium. So I would say about right here. So everything to the right of this time, this is our time. T could be in seconds, could be in hours, could be in days, depending on the reaction. And this is my concentration over here. Okay, whoops, it's an O. Concentration is on the y-axis over there. And so for this example, I drew it opposite of last time on purpose. The A decreases a certain amount and then it stops. The reaction reaches an equilibrium. This K, the equilibrium constant here, and we put a little C down below, subscript C for concentration. It's going to be products, that's B. The concentration of this guy over my reactant A. Okay, and you guys will see for this one, A ends up being higher than B. So this ratio for this problem is going to be, if A is a bigger number than B, that makes it a fraction. It's going to be less than 1. 1 is greater than this ratio. And that tells me that A is big and B is small. Okay, so here is our equilibrium. Now, what we can do is once we've reached this point right here, everything to the right is at equilibrium. If I mess with this system, this balance point where nothing is changing by adding something, let's add a reactant. So I'm going to draw that in blue so we can see it. If I all of a sudden, let's say at this time, I increase the concentration, so the blue line is immediately, it's going to go straight up when I dump a bunch of A into the equilibrium. Then it's going to try to adjust to get rid of what I just added. So you're going to see it go back down again. It's like a mini version. Okay, and actually I should have drawn it up a little higher. It's like a mini version of over here. It decreases to lower what I just added to it. What's going to happen to B? Well, B stays the same, but it's going to slowly increase a little bit, and then we'll reach a new equilibrium where they're at their balance point again. So A will be just a little higher, and then B will be a little higher, but they will come back to being constant. So the ratio will go back to being the same. The equilibrium constant will be the same. Okay, so this one will increase slowly until it reaches a balance point. All right, so what happens? Basically, whatever side we add to, if you add to the left, that's a reactant, it's going to shift the opposite way. And I need to finish these notes, so let's do that. Adding A or B, so this is a different equation than this one up here. So ignore this guy for now. Let's get rid of it. So looking at this reaction in our notes, and there we go. Highlight that. Oh, yay. Highlight yellow. There we go. For this reaction right here, if I add A or B, it's going to try to get rid of that. So I just increase their concentration. It wants to go back to the equilibrium, so it's going to lower. So that means it has to shift to the right. Shifts to the right to the product side. So we started with a certain amount of A, B, and C, and D, and they were in balance. If I increase this side, it's like if I had a literal balance where the two were level, and I add a whole bunch of reactant, that's going to throw the balance off. How do I regain the balance point? Well, some of this has to turn into this, so it's going to shift towards that side. Hello, whoever joined us. Okay, so it's going to shift until they regain their balance, until equilibrium is reached again. So adding to the left makes it shift right. Adding to the product side, if I was in my balance point and I add product, now I have too much product, it's going to get rid of some of that by shifting towards the reactant side. Last time you guys saw my chickens, today you guys get to hear them. They're being extra annoying right now. Okay, so it shifts to the left if I add product. Whatever side you add to, it goes the opposite way. Okay, so let's look at a real example. Nitrogen and hydrogen come together and they rearrange and they make ammonia, NH3. What direction will it shift if I increase the concentration of H2? So if I add to the hydrogen, that's a reactant, which way will it shift? It goes the opposite, so it's going to shift right. Okay, what about if I add NH3? If I add to the product side, so I have my balance point, and then I add a whole bunch of product, it's going to shift to the reactants. It's going to shift left. So adding hydrogen makes it shift right, and adding ammonia makes it shift, NH3, makes it shift to the left to get rid of that added ammonia. Okay, it wants to regain its balance by reducing whatever we did to it. It's going to try to undo that change. So whatever stress we add to the system, it tries to relieve that stress by shifting. So what direction will it shift if I increase hydrogen in my new equation? Here's our new equation. Hydrogen is a reactant, so it's going to go to the right. Okay, it shifts to the right. And if I add iodine, I2, that's also a reactant, so it also shifts to the right. Okay, so that's pretty easy. You add to one side, it goes the opposite way to relieve that stress that you just caused. And what about temperature? Temperature is just as easy because you guys remember, let's look at our examples down here. Whatever side the kilojoules are on, that's our heat energy, tells you what kind of reaction you have. So looking at this first example, let's call it example 1. Example 1, the 92 kilojoules are a product. That means they're coming out. That means it's exothermic. So the first one is exothermic and heat is a product. Okay, in this equation down here, example 2, the 510 kilojoules is on the left side, so that makes it a reactant. That means it has to go into the system for it to react. It's endothermic. So this is exothermic, heat's on the right. This one's endothermic, heat is on the left. And if we treat the heat as a product or a reactant, it's exactly the same as what we just went over. If I add increased temperature, if I add heat, and it's exothermic, this is going to shift to the left because it's giving off heat. So if I add heat to it, it will go the opposite way. It's actually going to shift left. And another way we could think about it, this might be a little confusing, but the reverse of this reaction would actually be endothermic. So if I add heat, I'm going to cause the reaction to go the opposite way because ammonia with heat breaks apart into hydrogen and nitrogen. So if I add heat, I'm shifting it to the left. I'm shifting it the other way. Okay, and then down here, it's the opposite of that because heat is a reactant. So if I increase the temperature, if I'm adding heat to this one, now I'm increasing the reactant side. It's going to shift to the right. Okay, and so water splitting apart into hydrogen and oxygen. Water's more stable. Okay, so that would be an endothermic reaction, and you have to add 510 kilojoules to force that reaction to go. So if I'm increasing the temperature on this, I'm going to let more hydrogen and oxygen be formed. So it's going to shift to the right, okay, if I increase temperature. And then decreasing the temperature, you're removing the heat. So if I lower the temperature of this one, I'm removing from the right-hand side. It's going to replace the heat that I took out. Think about it as when this reacts, it gets warm. If you were to cool it off by, let's say, putting it in cold water to cool the reaction off, that means that it can actually keep producing more and more heat, and you're removing that heat as it's forming. So when you lower the temperature over here, it can replace this heat by keep going to the right. So if I remove heat, this one shifts to the right. This one, if I remove heat, it doesn't have the heat that it needs to split apart, and these will actually come together. So if I remove heat from this second example, it shifts to the left. I have less energy for the water to break apart. These hydrogen and oxygen molecules are actually going to come together. It's going to shift to the left to replace the heat that I'm removing. Okay, so these two are essentially the same thing, changes in concentration and changes in temperature. You just need to know whether heat is a product or a reactant, and then you can treat it just like concentration up here. Whatever side you add to, it goes the opposite way. Okay, pressure is totally different, and basically the last thing that we have to understand, pressure, this is really important. There it is. I'm going to highlight it. It only affects gases in a reaction. Because if you have a solid, you could put a solid under pressure, the little atoms are already touching or the molecules are already touching, they can't get any closer. So when you put 2 atmospheres of pressure on them, it does nothing. 3 atmospheres does nothing. You would have to have an insane amount of pressure to affect the solid or even a liquid at all because they're already touching. Okay, so it only affects gases. If you put just a little bit of pressure on a gas, you can take those molecules that are really far apart and you can move them a lot closer together. So pressure affects gases only. And this is also really important. The total number of moles of gas on the left has to be different than the total number on the right-hand side. So we'll see an example that explains that in a second. If you have more pressure, okay, so picture our little gases. Ooh, let's draw our cylinder over here. Okay, and we have the lid on this guy that is able to go up and down on this system. So this moves up and down, so I can very easily increase the pressure if I just push that lid down, right? And I'm going to draw my little molecules. Let's draw them. I'm going to draw them green. And let's make them big. wish these could be nicer. Close enough. Okay. So there is my system, and let's say this is our A, and this is our B. Yeah. This is a different example than the one in your notes, but that's okay. Okay, B is going to be a solid, just to make these very different. So if A is turning into B, if the green one's turning into the red one, what is pressure going to do? If I lower the lid down, okay, so if I squish them down, what's going to happen? Well, these are going to be closer together. They're going to be more likely to form my solid, my product. Okay, so the moles of gas, if you increase the pressure, they're going to try to shift to reduce the pressure in the container. They want to undo the stress that we are causing to the system. So if you squish them, they want to take up less space, and they'll shift towards the side that takes up less space. So if this was A turns into B, then more pressure means it's going to turn into the solid down here. So it's going to shift it towards the product side. It's going to shift it to the red side. If I were to, let's get rid of this guy. If I were to give it more space, let's say I took this lid and the sides kept going up so my gas doesn't escape, and I raise the lid up, I'm giving them more room to spread out. That's going to lower the pressure way down. So it's going to shift in a way that kind of increases that pressure back up again. So if I raise the lid here, then these spread out even more, and this solid, more of them will turn into my green reactants, and it's going to take up more space as a gas. So this will actually shift towards the green molecules if I let them expand more. Okay, hopefully that makes sense. Let's look at some real examples. So let's say I have my nitrogen reacting with my hydrogen and making ammonia here. We need to look at the total number of moles of gas. So on the left side, there's 1 mole of gas here, 3 moles of gas here for a total of 4 moles on the left. And here, there's only 2 moles of gas on the right-hand side. So if I have more pressure on this system, if I had this balance point between these guys and they were all happy and they've reached their equilibrium, every time a reaction happens, the reverse of that reaction also happens, so they're at a balance point. And then all of a sudden I put them under pressure so they're closer together, they're going to shift to get rid of that added pressure. So which way will they shift if I increase the pressure here? They shift to the right. The right side of this equation takes up half as much room as the left side. Okay, I just thought of another way to explain it. So remember in chapter 11, we learned that 1 mole of gas, I'm going to write it over here. 1 mole of gas, and it has to be at STP, but it doesn't matter what gas you have because they're all spread out so far apart. Any mole of gas will take up 22.4 liters of space, which is a lot. So 1 mole is 11 2-liter bottles. That's how much you would need to hold that 1 mole. So if I have 4 moles, that means the left side of this equation takes up, what is that? Times 4, it's like, can I just call it 89 liters? The left side is going to take up that much. The right side, I could do this math in my head. The right side is just 2 moles of gas, so it's going to take up twice as much, so 44.8 liters. So the right side takes up a lot less space than the left-hand side does, and that's why when you add pressure, it's going to shift towards the right. Okay? Less pressure if I make the container bigger so the gas molecules can spread out farther apart, then this will have more room. It's going to break apart into its nitrogen and hydrogen components, and it's going to take up more space. So if I lower the pressure of that one, it's going to shift to the left. Okay. And let's look at this one. We have water, hydrogen, and oxygen. And I'm going to draw those guys. So we have our little system here. I do not like how big I left this. It's okay. All right, so there's our little container with our little piston that can go up and down. We have oxygen. Let's say, how many should I draw? Let's draw 4 water molecules. One. Oh, dang it. Being really big. Here's my oxygen. 2, 3, 4. So there's my water in the gas phase, and then I have, we're going to have to make the hydrogens blue and just a little smaller. Let's see if I can do it. That's all right. Pretend that's touching. Not too shabby. Okay, so if I have 4 moles of this H2O, that means I also need the 4 of the hydrogen. So there's H2, 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 and H2. And I just need half as much of the oxygen. Red, bigger. Okay, so if I have all of this bouncing around in my container, it's reached equilibrium where these guys will bump into each other. The hydrogens will split apart, the oxygens split apart, and then I have another H2O, but then another H2O breaks apart and the 2 hydrogens come together and that oxygen will find the leftover oxygen and we'll have another O2. So every time one reacts, one unreacts. If I increase pressure on this guy, so if I take this and lower this lid down, it's going to shift towards the side that takes up less space. That means that it's going to make more water. So these will react and make more water molecules, which take up less space. Okay, and then opposite, if I raise the lid up, I give it more room, I'm lowering the pressure inside, the water can split apart more easily and form hydrogen and oxygen to take up more space. Okay, so here's some for you guys to try. Which direction will it shift if we increase the pressure? Looking at this, you have to remember that this solid doesn't count. So add up the moles of gas on the left and add up the moles of gas on the right. If I increase the pressure, which direction will it go? Let me give you a second to think about it, and I'm going to pop back over here and see. We have no questions. Okay. Oops. Okay, so if I increase the pressure on this system right here, it's going to shift to the left. The left side has fewer moles of gas. It only has 6 moles of gas, takes up less space than the right side, which is 12 moles of gas. If I increase the pressure on this system, what is going to happen? Anybody know? If I increase the pressure on this, that's a trick question. How many moles of gas on the left? 2. And on the right side? Also 2. So neither side would relieve the stress. So you're just adding pressure on the whole system and it doesn't shift either way. Okay, trick question. And then also kind of a trick question. We didn't know that catalysts speed up the rate of the initial reaction. So catalysts, we have to go way back up here, would cause these slopes, whoops, this guy, and let's make it this guy. So a catalyst would do this. It would speed up this initial rate, but then it's going to level out just like it did before. So this thicker line would be with a catalyst, and the red one would just go up faster. Would go up faster. So the rate would increase, but then it would also level off. So it reaches equilibrium a little sooner, like right here-ish. So it'd reach equilibrium, but then the equilibrium is not affected. So if I add a catalyst over here, it does nothing. Once it's at equilibrium, it's going to speed up the forward and the reverse reaction rate, and nothing happens. Okay, they just help reach equilibrium faster. They have no effect on the equilibrium itself, or the constant. K stays the same. And that, I believe, is it for the chapter. Okay, so we need to know shifts right or shifts left. And actually, I was going to go over some of the problems with you guys. Did I pull them up? There they are. Okay, so this is one of the worksheets for the chapter. And all you have to do is type L or R right here to tell me which way it goes. I don't know if it's left, so let's get rid of that. Okay, so you have to balance the first 5 equations before you start. I'm going to do this one since we already talked about it anyways. I need 2 hydrogens, and I will make 2 waters, and now everything's balanced. So balance it, and then it says increase in pressure. If I increase the pressure on number 1, the left side has 3 moles of gas, and the right side only has 2. So an increase in pressure will actually cause it to shift to the right. Okay, so you're going to do the rest of these guys. Looking at, remember, solids do not count for pressure. You're only looking at the gases, and liquids do not count either. What about aqueous? Aqueous is dissolved in liquid. So adding pressure won't make, like a salt, for example, will not make the salt dissolve more. So pressure has no effect on aqueous either. Okay, for temperature, if I increase the temperature of these guys down below, you have to look at what side is the heat on. For number 6, the heat is on the right. It's a product. So if I increase the temperature, I'm adding to the right-hand side. Whatever side you add to, it goes the opposite way. So this one is going to shift to the left. Okay, and you guys can do the rest on your own. I remind me to go back and take these out of the worksheet when we're done, so you guys can do all this. If I add water to these reactions, oh, I see. So water is either a product or a reactant. So you're either adding to the left or the right of the equation, and then you have to tell me which way it goes. So for number 11, water is here. So if I add water, I'm adding to the product side. It's going to go the opposite way. It's going to shift to the left. It shifts left. Okay. And number 16, removing water. I'm taking away one of the reactants or products. So for 16, water's on the left-hand side. If I take water out, it wants to undo the stress of removing the water by making more water. That means it has to shift to the left. And I just noticed these are all single arrows. They're supposed to be double. I'll fix that. Okay, so if I remove water, it shifts to the left. Okay, what about lowering temperature? If I remove heat from this one, I'm taking away from the product side. It's going to make more heat to replace what I've taken out. So this one will shift to the right. And this is a trick question. I'll let you guys think about that one. And then lowering the pressure, make sure you look at the gases. And these are not balanced. You got to balance these ones also. Balance. Okay, so get those balanced and then do those problems. So this one, this worksheet, it looks like 30 questions. It looks like a lot. It's really not. It's just left or right. Right. I'm going to stop recording. You guys can ask any questions that you have.